got his Bachelor's of Science from the Chinese University of Hong Kong in 91. And then in 91, actually, we went to UC Berkeley together for a PhD program. And we were both students of Professor Zunino. And we graduated the same year in 96. Actually, we just went back to Berkeley for Zunino's 90th birthday, Bruno Fest, earlier this year. So we had a great time in Berkeley, and after that, he did postdoc in various places until 2001. He went to Durham University as a lecturer, and he came to Tsinghua University in 2002. And in 2004, he went back to Durham again, then became a chair professor of mathematics at Durham University. He returned to National Tsinghua University last year, and so here he is now. He has a long list of honors and awards, but he's modest. He didn't want me to read the whole list, so I just selectively read a few. He's a fellow of the Institute of Physics in the UK and fellow of the Higher Education Academy, and also he got the EPSRC Advanced Fellowship. And he's also receiving this Outstanding Scholar Chair Award from the Foundation for the Advancement of Outstanding Scholarship last year. So we're very happy to have Chung-Sen to give us a talk today. Let's welcome him.
Thank you very much for taking this nice introduction. And thank you for all of you today. I'm very glad to be here to give this colloquium. I understand it's a joint colloquium, so many of you probably certainly are not theorists, and so I will try to keep the technical details as minimal as possible. So my goal is to introduce you about what string theory is and what are some of the novel properties of symmetries and geometries in string theory. So because string theory is a theory about strings, about particles, so there are a number of interesting phenomena, especially in geometry and symmetry aspects, which you cannot see in particle theory. So those are my aim to talk about today. So this is a content, the outline of my talk. The talk will be basically consist of three parts. So I would first give an idea about what string theory is, and then talk about those a selection of example of geometrical and symmetrical properties in string theory, and then try to end with some conclusions. Of course, the conclusions are just chosen by me, so the subject is still developing. So what string theory is? So then let me start, go back in history to about the end of the 19th century. So at that time, there's this famous guy here, is Kelvin. He's a British theorist. So he in a meeting, he proclaimed that we are almost at the end of theoretical physics, apart from two small clouds which are at the horizon of the sky. So the two clouds he referred to are related to these two experiments. So this is the Michelson-Morley experiment, which you should be familiar with. This is the beginning of the theory of special relativity. So the failure about the search of Noether. And then this is the picture about blackbody radiation. So that's this experimental curve, the one black. I think it stopped working. So is there something physical? I can just use the physical. This one? Yeah. You can see that? So that's a black curve, which is the curve by experiment. But if you apply the theory, so you apply thermodynamics to electromagnetic theory, then you get this famous ultraviolet divergence due to Rayleigh and Jeans. So at that time, it's understandable why people have this kind of feeling that theoretical physics is close to the end, even though you see some problem with your theory. The reason is because at that time, of course, we know there's a golden time of thermodynamics and electromagnetic theory. People have understood how to make electromagnetic wave, how to make signal communication. And because of thermodynamics, people can start to use engine to build a factory and to conquer the world. So there's a great feeling about that's the end. We have finally conquered theoretical physics. But of course, we know now these two experiments, the failure to explain this difficulty from experiment, pointed to the two main development in the 20th century physics, namely special relativity and quantum mechanics. So what do we learn from this lesson? So I think one lesson I learned is that, at least I think we learned, is that you should not ignore any crash, especially the crash is theoretical in theory. So if you try to apply theory and try to apply your theory to some unknown domain, and then you find some crash, something you don't understand, so don't ignore it. Could point to some new physics. So in those two examples, in the case of blackbody radiation, you try to apply electromagnetic theory and thermodynamics together, and then you find a problem with ultraviolet divergence. And for the NERDA, you want to try to apply mechanics on combined mechanics and electromagnetic theory, and then you find you need some unknown properties for the NERDA to explain the propagation of the electromagnetic wave. So whenever you have a crash, don't ignore it. And we can always learn something when you try to resolve the conflict. Certainly this is true in the real world. When you have a car crash, for example, the insurance company always earns something. No matter which side wins, there's always something you can earn. You can learn, and you can earn by resolving the conflict. So it's also the same in here. So I wrote a number of more examples apart from the two I've shown you in the previous page. So for example, you may know that the prediction, the existence of antimatter actually was purely a prediction from theory, from thought experiment of Dirac. It's much earlier than any experimental effort. So for Dirac, he just tried to combine special relativity and quantum mechanics. And you know, in special relativity, you have a energy relation like E squared equal to P squared plus M squared. So yeah, thank you. So you ought to have a negative energy solution. So is it a big deal? You may say, okay, we can always stay with positive energy. But no, because special relativity mixes momentum and energy. So whenever you have line transformation, they mix together. So you cannot avoid a negative energy solution. And once you have a negative energy solution, there's a problem, because the world cannot be stable, because no matter what energy you have for an atom, the atom will always try to spontaneously decay to the lower energy state. So that's a catastrophe again. For this reason, Dirac thought very hard, and then he came up with a solution to introduce a Dirac sea to fill up all the negative energy state with electron. And that's how we come to this great conclusion, great prediction of antimatter. And it's not just antimatter, it's also the first prediction about a new particle in the world. So I think that's a great part of history of theoretical physics. And also UV divergence in QED, the same. If you want to apply quantum mechanics with field theory, in this case, a field theory of the electromagnetic wave, then you find divergences. And then resolving these divergences, again, in this case, earn Feynman and Schwinger and Tomonaga a Nobel Prize. And we have learned now a lot about renormalization properties of quantum field theory because of this trying to resolving the divergences. So never underestimate a conflict in theory. So now, what's the status today after 100 years from now, from 19th century? Now we have the standard model of elementary particle physics, which explain the world very well with a number of parameters. You can explain a wide range of phenomena and a wide range of interaction, strong interaction, and electromagnetic interaction, all in one unified language in terms of gauge theory. So there's a brilliant success. And we also have Einstein theory for gravity. So the Einstein gravity actually has been tested and has been applied to an unimaginable accuracy. relating to everyday life even. For example, the fact that your GPS system rely on the accurate prediction of generativity, and only after you have taken into account of those effects, we can have an accurate working GPS system. So these two theories work remarkably in their own domain of phenomena, namely gravity or elementary particle physics. But when you try to combine the two together, that's a problem. What do I mean by combining the two together? Which I mean, for example, the theory of Einstein gravity is actually a classical theory, and the standard model is based on a framework called quantum field theory. If you want to promote the Einstein gravity theory using the same framework of quantum field theory, then there's a fundamental problem. Nobody knows how to use that framework to write down a successful and consistent theory of quantized gravity. So the quantization of gravity remains one of the most important problems in theoretical physics. So obviously there's a certain kind of problem there. We know that two theories work very well, but when you put them together, we need to modify or extend our previous concept. Just like the example I have shown you, when you combine theory together, especially when you see a crash, then usually there's something there waiting for you to discover. So string theory now come up as a promising candidate for a theory of quantized gravity, quantized gravity. So let me just first start from the very beginning, tell you what string theory is in a very simple way. So string theory is, the best way to understand what string theory is just to understand what quantum field theory is first. Quantum field theory is combining special relativity and quantum mechanics on the system of quantum particle. So that gives you quantum field theory. So just combining the two fundamental principles of the 20th century of physics, 20th century physics, special relativity and quantum mechanics, apply it on the system of quantum particles. So the representation is in terms of quantum-like particles, then you get a theory of quantum field. So all the rest are technical details. You see textbook, loads of textbook talking about quantum field theory. But in a nutshell, it's just that. The rest is just development. Depending on what kind of particle, what masses, what spin, and what kind of interaction, then you can write down a lot of chapters on quantum field theory. Now, string theory is similar, but there's one main difference. String theory doesn't touch the fundamental pillar of physics. You still keep special relativity and quantum mechanics. The only thing you change is that you say now instead of particle, quantum particle, the fundamental object is not particle without any size, but it's a string with a finite dimension. So that's the only thing we change here. So we don't change the physical law, right? We just change what the object, the system. Like we are not talking about ideal gas of particle, but it's ideal gas of string, right? That kind of thing. So it's a minimal extension of what we know about quantum field theory, but the outcome turns out to be quite dramatic. And this small change turns out allow you to, for example, quantize gravity and a lot of other new phenomena to unify. Well, this is the thing which I'm going to talk about. Yeah. So as a profound consequence. So basically, what changed after you make this? What's the difference there after you make this change from quantum particle to string? Is that for quantum particle, basically, you can characterize a particle by masses, a spin, and number of charges. So a small number of parameters, quantum number for the quantum particle. But for strings, you can have internal motion. So not like particle, you can only have translation and internal spin, but you can also have vibration for strings. So that's the main difference. So for string, you can have different vibration, and this different vibration, these harmonics of strings correspond to elementary particles of the world. So basically, there's a machinery in string theory which allows you to compute what's the masses and spin of the excitation of the string. And after you've gone through it, then you find you have a spectrum, an infinite number of particles with different masses and different speed. So in principle, it can contain all the particles we observe in the world. And in fact, you did the computation, and then you find, well, one of the excitation, in fact, is a massless and spin 2 particle state. And this fact tells you this has the same quantum number as a graviton. But of course, it's not enough to have this to say this is actually a graviton. You also need the interaction to know this is actually a graviton. So you can compute this from string theory, and you find that the interaction is exactly the Einstein. You can reproduce Einstein equation from string theory for this particle. So that tells you string theory contains gravity. So the history of string theory is actually a bit bizarre. In the beginning, string theory was proposed not as a theory for gravity, as a theory for QCD. Because at that time, there's a strong interaction, and strong interaction is too difficult for people, and people haven't understood how to deal with QCD. Right? That's before the asymptotic freedom were understood. So people developed different alternative theory, like this kind of phenomenological model, like a string, hoping that it will help to understand QCD physics. But then, because of this observation, due to Strack and Schwarz, basically, in '74, then they proposed that string theory is actually not a theory for QCD. So they make the goal much bigger now. So they claim that string theory could provide a theory for quantized gravity and also all the other forces. So to explain this last statement, you have to go back to the spectrum, and then first you find whether there's a spin 1 massless state, and then whether they have the same kind of gauge interaction correspond to the real world. And so all this can be, in principle, can be done. So of course it hasn't been done in a very completely satisfactory way, but there's nothing in principle which against you, which will forbid you to do that. So in principle, string theory contains all the ingredients to contain both gravity and other forces and all the matter particle. So all just contain as different vibrational mode of string. So what you think about as both as interacting particle, interacting gauge boson, and matter particle, in fact they are all different manifestation of the vibrational mode of strings. So in this sense, string theory unifies matter and interactions. So it's truly a unification theory, right? That was the status in the 70s. But of course, the proposal by Strack and Schwarz have met with a number of complaints and difficulties. And basically, resolving those complaints and difficulties lead to the first string revolution in '84. So the complaint and difficulty of the previous picture was that the previous construction of Strack and Schwarz was a bosonic construction. So it's a string which contains only bosonic degree of freedom. So that's no fermion. So, but on the other hand, if you want fermion, I mean, of course, you know the world, all the matter are basically fermion, apart from the Higgs boson. We need fermion. So that cannot explain the world because you just don't have all the fermion. And the other problem is that the construction of the bosonic string requires the space-time to be 26 dimensions. So this is something which cannot be easily explained. But for those of you who are more expert, have more knowledge about quantum field theory, you know we have anomaly in quantum field theory. And anomaly allow you to fix, for example, to fix the gauge group or to fix spectrum of particles. So for those particular combination of gauge group and representation of matter, you have anomaly-free theory. So basically it's the same here. There's an anomaly associated with the Lorentz group of string. And only for a Lorentz group in 26 dimensions, all the anomaly are gone. So that's the reason why the bosonic string lives in 26 dimensions. Of course, at that time, or even now, we are still living happily in 4 dimensions. So we don't have any experimental reason to think we are living in 26 dimensions. So where are all these extra dimensions? So that's a very, seems very bad, right? We are talking about something which we don't actually see. Another problem is that in the spectrum, actually I have not told you the whole story. In the spectrum, actually if you look at instead of looking at the massless spin 2 state, if you go lower in energy, you find a tachyon, which is a state with a mass square, negative mass square. So a negative mass square particle in the language of particle is called tachyon. In the language of field theory, it's just a potential which is inverted, so it's not stable. So it means the vacuum of string theory is not stable. So these are the problem already discovered in the 70s, and resolving them lead to the I said already lead to the first string resolution. So the resolution, of course, I cannot tell you all the full details, but actually it's also quite simple to understand. Without fermion, that's fine. Then you just introduce the fermionic component of the string. So you turn it into a fermionic string, then you can have fermion. Now for tachyon, it's a property of supersymmetric theory. We probably heard about supersymmetry, which is a symmetry relating boson and fermion. In a supersymmetric theory, the vacuum energy is zero. So tachyon are automatically removed. So introducing supersymmetry, introduce both the fermion and remove the tachyon. So it does two things for you, solve two problems already. So at this stage, string theory starts to become superstring. So today we call string theory, but actually we are talking about superstring theory. It's always come with supersymmetry in order to resolve those problems. About 26 dimension, well, of course we have never seen 26 dimension, but could it be possible that some of these extra dimensions actually are so small, they curve up to very small dimension, so you cannot actually easily discover it. It's just like if you see this stick, there's one dimension which is this longitudinal dimension, and also there's a circular dimension. Of course, now you can see this is two dimensions because it's a cylindrical surface. But if it's very far away, then probably you can only see the line, and then you don't see the circular dimension. So in this sense, the circular dimension is curved up, and you cannot see it unless you are very close. Unless you use a microscope, you look very close. You use a high degree to probe it, right? So the proposal is that well, for superstring actually live in 10 dimensions because the anomaly is different. There's different some additional contribution from the fermion. So the proposal is that 6 of these 10 dimensions are very small, and they curve up into small compact dimension, so you don't see it. And so that leads us to the 4 dimension of the world. Yeah. Why? Yeah, it's based on some technical calculation, but the basic reason is I said there's some inconsistency in the theory, which is called anomaly, and those anomaly, those inconsistencies come from the some property of generic property of the theory. We want to it's actually quite difficult to understand normally, but there's some inconsistency in the theory unless you formulate the theory in this dimension or this dimension. If you have experience with anomaly in field theory, then it's the same. In that case, you constrain the gauge group, the rank of the gauge group, or the representation. So here, this 26 and 10 is basically the dimension of the group, the Lorentz group we're talking about. So at 84, after we introduce supersymmetry, then people find that there are only 5 types of superstring theory you can write up. So the 5 types of superstring theory are called type 1, type 2A, type 2B, or this HGHO, which is called heterotic, with a EH called EH gauge group, or a heterotic with SO32 gauge group. So these are just a Lie group with a special properties, which is called EA cos EA or SO32. But the details are not important, right? So basically, the main message is that there are only 5 string theory. So it's not like gauge ordinary non-abelian gauge theory. You can have a gauge group with rank arbitrary S to N, or you can have an arbitrary method with different representation, so long as you satisfy anomaly cancellation. Then that's a viable, there will be viable phenomenological model. But here it's different. There's only, after you impose all the string consistency conditions, there's only 5 which came up, and they have a fixed property. They all have a different symmetries and gauge symmetry, but they are fixed. So for example, this HGHO, they come with non-abelian gauge symmetry of this type, some E type or SO type. And the rest, for example, the type 2 thing doesn't carry any gauge group. Right? And then the type 1 is something, I don't want to tell you the detail, but it's another construction which, again, there's no arbitrary parameter you can tune, no rank or no freedom of putting any representation. So in a sense, we start from some very basic assumption, just modify one particle to string, and then you have come up with a construction which is so restrictive. You only have to find a number of candidate theory. Right? So the only parameter which are left in this theory, there's a mass scale, which is called the tension, or the mass parameter of the string theory. Just a scale. So of course, in any theory, unless it's conformal field theory, otherwise there must be a scale. So there's a scale. So this scale eventually will give you the scale of the masses of all the spectrum of the string. And then the theory is interacting, so there's also a coupling constant. So there's only two parameters. Otherwise, those theories are completely fixed. So at that time, people actually got excited because that's the first time it seems to indicate that we are converging to a unique theory, a theory which can unify all the matter interaction and which can explain the world, and also is unique enough. You don't have to tune any parameter. There's a possibility, or at least there's a hope. One of those theories will actually give the world, give you everything in the world we observe, and everything can be calculated. For example, all the CP parameter, or I don't know, neutrino masses, all those things can be calculated, could be in principle from one of those theories. So string theory at that time started to pick up a name called theory of everything. Of course, it doesn't mean theory of everything, because there's no way you can explain biology from this. But it's everything enough so that people start to give it a very powerful name. All the theoretical physics. Yeah. Well, of course, it's a wishful thinking, I would say. Even if you understand everything about quantum mechanics, it's still very far away from being able to use quantum mechanics to calculate something like the properties of a complicated system like the car, right? It's just too many steps in between, and to have a fundamental theory is one thing, and whether you can use that to calculate something at our energy scale is another thing. So, but at least there was a very enormous hope at that time that we could actually arrive at the theory of the fundamental theory of nature. But then obviously, if you are thinking in this kind of frequency, then there's two questions which come to mind immediately. First, if we are really thinking about the unique theory, then certainly we don't have a unique theory. We have at least 5 theories in the previous page. So why are there still too many? And which is the one which explains the world? And also, there's a problem with the so-called uniqueness of vacuum. What it means is that we start from 10 dimensions, and then we need to compactify it to 4 dimensions. So this process of compactification to make 10 dimensions small, right, has a lot of solutions, basically. You can have a big 6-dimensional manifold of a shape, of a different shape, different color, and different twist, different topology, right? And more technically, you probably heard about Yao Chen Tong. So that's his manifold. So these are Calabi-Yau manifold. They're basically millions or tens of millions, or I don't know the unit, you can call it Google million of manifold. And why any particular one are chosen to explain the world? What about the other one? Are there any dynamical reason to pick one other than the other? If you don't have, then we are doing phenomenology. I mean, I have no sense of I mean, we want to understand. The question here is different. We want to understand why the parameter take those values. So we need to understand why a particular manifold are chosen other than any other one. So in '84, people understood have understood supersymmetric string theory, and then have the hope that it could be the theory of everything. But then people also realize there's a limitation. You need to at least understand these questions before you can actually claim string theory. Well, not claim, but at least you can make a more reasonable justification that string theory could be a theory of everything, right? But so trying to understand or to address this question, basically occupied the next 10 years or so until '95, and then there's a lot of these questions got